Recall that previously we mentioned that given a function field of transcendence degree 1 over an algebraically closed field, we can recover a unique projective non-singular curve with that function field. As I said, that unique non-singular projective curve is gonna be in bijection with the discrete valuation rings contained inside this big K. So before moving on to give an explicit construction of this, we want to give some motivation for its definition. So in this video, we want to explain the first idea, which is how to view points on a curve C as subrings of its function field. So given a point P on a curve C, to remember which algebraic object best capture the local picture at P. Well, to understand the local picture at P, the most natural thing to consider is the ring of regular functions at P. And recall that this is a generalization of the notion of rings of germs of holomorphic functions or germs of smooth functions, right, in differential geometry and in complex geometry. To refresh our memory, let us just quickly do one example. So let us consider the affine Kapp's curve, view as a curve in a 2K. Let us compute the ring of regular function at the origin. And let us recall quickly that in the case here of an irreducible affine plane curve, by a function on C, we mean the following. Roughly speaking, a rational function on any K variety is just a map from some open subset of the variety to K. That could be given locally by a rational expression. In our case though, the rational functions could also be given globally by a rational expression, so let us use that as a definition. So let us think of a rational function on C as a map from an open subset of C to K that could be given by a rational expression, i.e. by a quotient of polynomials. That is, there should exist some polynomials f and g such that for every point P in this domain of phi, the value phi of P here could be given by evaluating this quotient f over g at the coordinate of the point P. You might ask, well, then why don't we just define a rational function on C to be a rational expression on C? Why don't we just identify phi with the expression f over g? Especially since they agree at every point on the domain of phi anyway. Well, the problem is that two different rational expressions might define the same function on C. For example, here y squared is equal to x cubed on C. Or to put it another way, both the expression 0 and the expression y squared minus x cubed define the constant 0 function on C. Alright, so again let us think of a rational function on C as a map on an open set of C that could be given by a rational expression. We say that a rational function is regular at a point P on C if it could be given by a rational expression that could be evaluated at P. That is, if it could be given by the ratio of polynomials f over g such that g does not vanish at P. In our example here, we see that the rational function defined by this expression is regular at P because we can evaluate this at P. This denominator does not vanish at P. Whereas we see that these rational expressions cannot be evaluated at P. Though be careful, from that you cannot conclude yet that the rational functions defined by these are not regular at P, because they might have different expressions, but let's not go there. So we see that the rational functions that are regular at P are given by quotient of polynomials f over g, where g does not vanish at P. Right? So it does not lie inside the ideals of functions vanishing at P, which in our case here is the ideal generated by x and y. And now be careful here. So from this you might conclude that this ring then must be kxy localized at x comma y, i.e. It's whatever we get by inverting all of the polynomials that do not vanish at the origin. But as we said, two different rational expressions might define the same function, so we need to have an identification. And thus the correct answer is that this ring of regular function here is the localization of this coordinate ring of C at the ideals of functions vanishing at P. Alright, so that's a brief review of the notion of the ring of regular function at a point P. Coming back to our discussion, as we said, for every point P we can associate this local ring which captures local information at P. Now, the natural question is, does this ring determine P uniquely? That is, if the local rings at 2 points P and Q on the curve C are the same, does it mean that P must be the same as Q? And we'll answer that in the next video.